Colin, is that right? Yes. Got your test here. So first, let me talk about the schematics for these transistors. So remember that when you're looking at these PIP 120 transistors from the front, and the front is the side with the black. When you're looking at the black box, on the back it all looks silver. So it'll look something like this. You'll see the black box there. And then you'll see the silver with the hole in it. That hole, by the way, is for putting a heat sink into it if you're worried about your thing heating up. Most of you won't have to deal with that. And you have the 3 terminals coming out. This one is the base. This one is the collector. And this one is the emitter. And in a schematic diagram, it looks like this. And this is the base. This is the collector. And this is the emitter. So that's how the schematic relates to the physical thing. And if you want to use this transistor to, so let's say that we want to power some device, some relatively high power device using one of our output pins on our board. So let's say that we have, so let's say that this is our pin 7. I don't know why I always use 7. It's just right in the middle somewhere. And then this is our ground. And we want to use this to power some device. So this isn't, so I said power, which really is not accurate. The board is not going to power this big device. It's just going to signal when to let the power through and when not to let the power through. Okay, so really like a separate battery or some other source of voltage is going to power the device. So the way this is going to work is we're going to go from pin 7 through a 10,000 ohm resistor. Might as well just always use the 10,000. It's quite a small current that you need here. And then it's going to go from there to the base of the transistor. And then from the emitter of the transistor, we're going to go to the ground. Okay, so right now, what this does, I haven't connected anything to the collector yet, but right now, when this pin 7 goes high, goes to 5 volts compared to the ground, what it does is it allows current to flow in the collector and out the emitter. Okay. And when we make this low, we put this at 0 volts, put it in the same electric potential as the ground. Then that closes that gate or opens the circuit. And so now no current can flow between from the collector to the emitter. So that's how we're using this pin 7 to signal current flow. And so anyone remember how much current I said these pins can handle on this Arduino board? it's about 20 milliamps, okay, which is pretty small. You can't power much with 20 milliamps. You can power an LED, but you can't do physical things that you would want to do with a robot, okay. On the other hand, the current that this transistor can handle going in the collector and out the emitter, that can get up to 2 amps. Okay, so 200 milliamps to 2 amps is a factor of 10. Is that right? Yeah. So you can have, if you're using this transistor, you can switch currents that are 10 times as big as you could if you were just trying to go from the pin. And that makes a big difference to us because with this, you can only power like an LED or whatever. Using the transistor, we can power even pretty big motors and generate pretty big forces and torques and stuff. Okay, so now we're gonna wire the device in. And I'm gonna make this a motor because why not? That's the most common thing that you'll probably want to do with this. So let's say that here's our motor. It spins this little shaft around, and let's say that this is the positive and this is the negative of the motor. And I'm going to use my battery over here. So this is the power source for running this motor. And I'm going to go from the positive to the positive of the motor. And then I'm going to go from the negative of the motor. So current, we're just trying to get current to flow from the battery through the motor. Bless you. The negative is going to go to the collector. And then, so since there's only, like, notice that there's kind of 2 positive terminals to a transistor, or the type of transistors we're using. This is kind of a positive terminal. This is the one coming from the signal. This is kind of a positive terminal. This is the one coming from the battery. But we only have 1 negative terminal. And so those have to be, you know, the negative from our power has to be the same as the negative from our board. And so that's why I'm going to connect from the negative of the battery. I'm just going to say that has to stay at the electric potential of the board, the ground of the board. Okay, so you always have to take the negative of your power source and put it at the same electric potential as the ground of your board. And the reason for that is just the fact that there's only 1 negative terminal for both of these 2 things. And then there's one other thing that we need to do since I made this a motor. Remember that we need to have a diode that only goes in the reverse direction. This is to keep magnetic surges from damaging the board. Did you know that electricity and magnetism are all like one thing? The problem, motors work on, so they work with this interaction between magnetic fields and electricity. And so when you shut off the current to a motor, there's a surge in the magnetic field, which causes a surge in current. And that's why you have to, protect the parts for whenever you have a surge in electricity to a motor. Okay, because there's a corresponding surge in electricity that can damage things. Want to hear an interesting story about electricity and magnetism? Everyone's like, we have to, I think. Anyways, I'll just not. Okay, so in the 1800s, mid-1800s, early 1800s, people were able to measure the speed of light. Okay, so that was just a measurement that they could take, and it's a tricky measurement to take because it goes so fast, you know. But they measured it pretty accurately. It's about 3.0 times 10 to the 8th meters per second. So what's that? 300 million meters per second. Okay, so that measurement was there. And then people started sort of figuring out the relationships between electricity and magnetism. And people figured out that if you took the equations for electricity and magnetism and made certain assumptions about it, you could come up with this mathematical form to it that was a wave equation. And so what you get is that you get a change in electric field that produces a change in a magnetic field that produces a new change in an electric field, new change in magnetic field. And this goes on and on like a wave pattern propagating itself. And this is an electromagnetic wave. Okay, so, and the math is super tricky on this. I've never worked my way through it or anything, but good mathematicians in the mid to late 1800s figured out that if you took this wave equation, you could calculate the speed that wave propagates through space. And at this point, there was no connection at all between electricity and magnetism on one side and light. But they did this calculation, calculated the speed through space, and just amazingly, 3.0 times 10 to the 8. And so that was the first inkling that anybody ever had that light is an electromagnetic wave. But it seemed like too much of a coincidence to not be. So everybody at that point hypothesized, like, hey, maybe light is an electromagnetic wave. And that's what it turns out to be. So I don't know. Cool. So light is an electromagnetic wave. All energy on Earth depends on electromagnetic waves because radiation of electromagnetic waves is the only way energy can propagate through open space. Other ways, so like if you think of energy propagating through like a pan that you have on a stove, okay? Like you heat up the bottom of the pan, eventually the handle gets hot, okay? Well, that depends on a medium that heat can transfer through. That type of heat transfer doesn't work through, say, space. Electromagnetic waves, though, don't depend on a medium to transfer them. So these electromagnetic waves, radiation, heat radiation, is the only way that the energy from the sun makes it to Earth. And it all happens at the speed of light because light is an electromagnetic wave. Okay. All right, so now I'm finally at your question. This, you didn't ask about this, but so now we want to put this in a schematic diagram, and we're going to use this form for it. Okay, this is the schematic for this type of transistor. So we are going to, so I'm going to write this as pin 7. And I am going to have it go through this 10,000 ohm resistor. So these are all symbols that you've seen quite a bit. And then it's going to go to the base of the TIP 120 transistor. Okay, are you with me on that? So the current coming from pin 7 goes into the base of this transistor. The arrow points to the emitter of the transistor, and that's going to go to the ground. So I'm going to put a ground symbol here. And now so now we have the schematic version of this pin opening and closing the circuit going from the collector through the emitter. And so now I'm going to go, so I have my battery over here. So the left is the positive and the right is the negative. And that battery is going, the positive of the battery is going to go through the motor. And I'll just write that as a circle with an M. So that's my motor. And it's going in the positive side here, out the negative side here. And so now we're going from the battery through the motor to the collector, out the emitter. We have to put the diode in. And the symbol for a diode is an arrow with a vertical line. So the arrow points in the direction you want to allow current. We want the current to go opposite the polarity of the motor. So there's our diode protecting the equipment. And then we want to go from the negative of the battery. Remember, the negative of the battery has to be at the same electric potential as the ground of the board. And so I'm just going to take the negative here and connect it to the ground. So that's a schematic representation of the, it's obviously cleaner to look at and stuff than the kind of messy semi-drawing of the wires. Any questions about that? As far as wiring a transistor, you can just pop the transistor. So if this is your breadboard, it's designed to fit right into these rows. So you can just take it and pop it right into place like this. And then those rows will let you connect to the base, the collector, the emitter there. Okay. Any other questions about the homework assignment? Do you have a question? No? Yes.
I don't know how to like download like these homeworks into the Google Docs, so I can then work on that. So all I've been just doing is like writing it.
Yeah, that's what I want you to do. I just want you to do it by hand.
Yeah, I just write it down on my paper, take pictures,
Right.
and send it.
That's perfect. Yep. Any other questions? Okay. Well, let's talk a little more about programming, Arduino programming, and then we'll do an example where we're going to have it so that you have an ultrasonic sensor that's detecting how far away an object is, like your hand or whatever. And when your hand gets within a certain distance of the sensor, we're going to turn on a motor. Okay. And you can imagine this is kind of the basis of any kind of robotics. You have a sensor measuring something, and when that measurement tells you a certain key bit of information, then you fire up a motor or do some action. Arduino programming. I said some of this stuff before. So there are two sections. The first is the setup section. And this is only run through once. And you can use this to define your variables. To declare Arduino pins as input or output. And so an example of this would be, let's say, so long is a type of, so this is just saying, so we're going to define these variables to do our calculations, and I'll talk about what variables are, but we have to say what kind of number we're looking for. And so long is a type of integer. So there's no decimal part to these numbers. So what this means is long is the type of number. So this, we would use this for big integers. And duration is the name of the variable. And so what we're saying there is anytime you put a value into this variable called duration, the type of number that's going to be is a large integer. Another one that we're going to use a lot is float. So let's call this one distance. So this is the name of the variable. And float here is the type of number. And a float is a decimal point. You know, it's a real number, so you can have a decimal on it. Okay, so if you're doing calculations with things, you usually want them to be floating point numbers like that. If you're they're doing the ball launching lab in physics 1, apparently. If you're getting input from a sensor, a lot of times you're going to want it to be type long. Okay, you're going to want it to be an integer. That's just the format of the number that it gives you. Okay, and then the second type, the second section is loop. So it's going to go one time through just in order of the statements that you have through setup, and then it's going to go into loop, and it's going to do that in order and then go back to the top and keep doing it until you turn your thing off. So this will go through the commands in order. And then go back to the beginning of the loop and repeat it again. And so most of the commands that you're going to use in your program are going to happen in that loop, because what you want your robot to be doing is constantly evaluating the environment and then using that information to do stuff. So, you know, look to see if there's a human to kill. If there's a human to kill them. Then it loops back, look to see if there's another human to kill, you know, and just keep going through. No killing robots, please. Okay. Okay, so another thing you need to know about is this idea of variables. And the word variables, I think, is a little misleading. It's not really like a variable in algebra. The way you really want to think of it is a box where you can store data. And based on what type of data this box, this variable, the way you've defined it, like if you define a variable to be a long integer, then any junk that's inside that box is going to be interpreted as a long integer. If you say that it's going to be a floating point number, then any data that's stored in that box is going to be interpreted as a floating point number. So the first thing you have to do is initialize to tell the program how to interpret the data in the box. So that is the thing that I did up here for this long duration float distance. That's initializing those variables. To put a value in a variable, in other words, to put data in this box, what you do is on the left, give your name of variable, and then an equal sign, and then on the right, put your value. In algebra, it doesn't matter which side of an equal sign, two things that are equal, it doesn't matter which side they're on. X equals 2 means the same thing as 2 equals x, but here it does matter. This is a syntax that you need to use, and what you're doing is putting a value inside your box. Okay, so this has to be on the left, and this has to be on the right. Okay, so for example, now we've defined distance as a floating point number. So I could do something now that I've defined that, put distance is equal to 1,231.84. I'm just making up a number, but that's a floating point number. And these are going to be important because this is how you do calculations. And we'll do some of that today, but so if you, for example, if your sensor tells you, if you use your sensor to tell you that an obstacle is 3 inches away, you might want then to turn a motor on at some value that, say, is 20 times that distance or something. Okay, so then what you would do is put the distance that you measured into a variable, multiply it by 20, and then use that new value to power your motor. Okay, so all calculations you do are going to be using variables. And then the last thing I want to talk about is conditional statements. So those are if, then, else statements. And so these are the ones you can, it's pretty easy to understand the importance of conditional statements like this in robotics. A lot of times we're going to say, if this sensor measures something less than 8 inches or something, then some action is going to happen. And so this if idea is how we're going to do that. We're going to keep evaluating a variable that's getting updated, and we're going to check to see if that variable value is less than 8 or more than 8. And based on that, we're going to do some action. So the syntax looks like this. So if, and it has to be lowercase. Let's say we have a variable length is less than 5. And now you use the squiggly brackets that define sort of, you can think of it as kind of statements in this programming language. Then what you would want to do is turn the pin value high. This is not computer code. This is just, we'll worry about the details of the computer code later on. And then you would end that statement. Then you could say, well, maybe we want to do something else if it's between 5 and 8 or something. So the way you would do that is else if, and in parentheses, you'd say, length is less than 8. And you might, turn a different pin value high. Okay. And then end that statement. And then, so let's see. So now the last thing would be, okay, we know what it's going to do if it's less than 5. Okay. If it's not less than 5, we'll do something else if it's less than 8. And then if it's not either of these, that means it's equal to or more than 8. And so then we can just use the else statement. In all other cases, maybe we'll turn all the pins low. So turn off the voltage at all the pins. Okay, so we're going to see all this stuff in our example today. Anybody have any questions about any of that before we, yes?
So the else if statement is saying if the first statement conditions are not met.
Correct.
Then it goes to that one.
That's right.
Okay.
That's right. Yes.
So I'm looking at some of the examples that were built into the Arduino program.
Yeah.
Some of them include constants for the name of the variables.
Oh yeah, so that's just a variable that's not going to change during the program.
Okay, so the constant is for the constant, and then is the int for an integer or
Yeah, int is for an integer that is not that's not big, So from some of the sensors, we're going to get values that are really, like, it's counting milliseconds, for example,
Yeah.
So if 5 seconds go by, we get a big number. And so or if 40 seconds go by, we get a big number, And so that's why we'll often use the long integer format. But if you're just talking about integers up into, the thousands or whatever, you can just do it as an integer. I'm pretty sure that the only reason you would use an integer instead of a long integer is memory, to save memory. I think it just a long integer takes up more memory space. And I don't think that's ever going to be a concern to us. So you could always just use long. Yeah. All these programming languages, when they were created, everything was about memory, like everything was about being stingy with memory. You could run out of memory really fast. That's not really the case with programming anymore. Like our ability to store data has grown so much over the last 50 years or whatever. All right. Does everybody have a kit at your table? Okay, I'm going to get one. So we're using the HC. Yes. Okay. SR04. So it has two things like this. These are both the pulse emitters and the detectors. And they look like robot eyes. And they function like eyes. So remember that as you're designing something cute later. And we have 4 pins. VCC is the one that's going to be attached to 5 volts on the board. Trigger is going to send the pulse. Echo is going to measure the time until the pulse returns. And then this is going to connect to the board's ground. So you can put this sensor on your breadboard. So let me draw the breadboard. So this is going to be our red and our black power rail. And then we have things like this. And I think you can just attach the ultrasonic sensor this way. So just put it across 4 of the, I think it's spaced correctly for this. Oh, we only need 4, not 5. Okay, so this is the VCC trigger echo, and this is the ground. And you can go from your board right now. Can I look at someone's board for a second? So we have the, so if you notice on the left side of your board, there is a pin that says 5 volts and a pin that says ground. So let's just, we'll connect this sensor to the ground and the plus 5 volts right now. So if this is the Arduino, here is our plus 5, and here is our ground. And we can just go, right now we'll go from the plus 5 to the red power rail. And we'll go from the ground of the board, whoops, wrong one, to the black power rail. Okay. And then you can go from the red power rail to the VCC. And you can go from the black power rail to the ground of the sensor. Are you with me on that? So then we have the power all taken care of. And then we'll use, I don't know, it doesn't matter what pins we choose. Let's choose pins 6 and 7. So let's say we'll use pin 6 for the trigger. Which way does it count, from the bottom or the top? It counts from the bottom, doesn't it? So let's use 7 for the trigger and 6 for the... So 7 for the trigger and 6 for the echo. So now you can go... so this is going to be my pin 7, and this is my pin 6. And I'm going to go from pin 7 to the trigger. And I'm going to go from pin 6 to the echo. And that's about all the wiring we need to do. And now go into the Arduino programming environment, and we're going to start telling this what to do. So now that in the Arduino programming environment, we have these two parts of the program, the setup and the loop. So and you don't have to type these, they're already typed in, but I have to draw it in here. So the first one says void setup, parentheses, and then squiggly bracket to start the setup thing. And what we want to do is, so the trigger is sending, when we give it the command, we want it to send a pulse of sound out into the world. Okay, so that is an output signal. That's us saying, do something, you know? And so the one that's connected to the trigger, we want that pin to be set as an output pin. Okay, as opposed to a pin that reads data. So I'm going to use this command pin mode, and you have to get the case correct. It's case sensitive. So it's lowercase pin and then capital M mode. And the trigger is connected to 7. So we want to set pin 7 to be output. And this output has to be all capitals. And to end this statement, semicolon. So now we're saying pin 7, as long as this program is running, it's not ever going to read anything. It's just going to take our instructions and go on and off when we tell it to. And then on 6, that's the one we want to read things. So we're going to use pin mode again, but we're going to make that one input. So 6, input.
Is this case sensitive, the pin mode?
Everything in this language is case sensitive. And then remember, this has to go in every one of your programs. We're going to say that communication between the program and the board happens at this speed. Serial dot begin. And then in parentheses, 9600.
Is that a capital S?
Capital S, yep. And then we're going to need a couple of variables. So I'm going to define them here. And I guess and this is just based on, what kind of calculations we're going to do, what the values come back with our sensor as, and we're going to make these both floating point numbers. So lowercase float. And our two variables are going to be duration. And then comma, and then distance. So we have these two variables defined. That's all we need in this setup. So once you have that, you can squiggly bracket and end that section. And now we're going to go on to the loop. So now all lowercase void loop. Squiggly bracket. And what we're going to do here is we're going to turn the voltage on so first we're going to send out a signal, then we're going to receive a signal. So to send out the signal, we're first going to turn pin 7 to voltage 0. We're going to turn it low. So that's the first thing. Whatever it's at, we want to start with it low. And the command here is digital write. And this is for pin 7, and we want to write it to low. So this command digital write for output pins, it's just our way of telling it, do we want low voltage of 0 or high voltage of 5 volts? So we want it 0 to start. And we want to pause for a very short amount of time. And so I'm going to use this command, lowercase delay, capital M microseconds. And we just want to delay for 2 microseconds before we do anything. That's no time at all, you know. But we're just kind of cleansing the palette of this thing before we send the pulse out.
What happens if you don't wait for 2 microseconds?
I think that try it and see. I don't know. I would guess that is just the amount of time to make sure that that command happens before you go on to the next command. Because when you go from, so all electronic things happen kind of instantaneously. They happen in one clock cycle or whatever. But physical things don't happen instantaneously. So so if we're sending out an actual sound pulse as opposed to an electronic pulse, we have to give little margins for things to happen. I think that's the idea. And then now we want to send the actual pulse, so we'll go digital write. And it's pin 7 again, and this time we want to go high. And our pulse duration is going to be 10 microseconds. And so we'll go delay microseconds again. So what we've done is we've turned the voltage low, waited just a second to clear the air. Then we sent out a 10 microsecond sound wave. And now we're going to turn it off so that that's the end of the pulse. And so now we've sent that pulse out. And now our job is to measure how long it takes for it to bounce back. And so now we'll say duration, lowercase duration. Remember, that's our variable we defined. That's a real number, a decimal number. And we're going to say what we want to put into duration is how long it takes to detect this signal. So we're going to, this is a function that's built in, lowercase pulse in. This one, we want the input pin to read this, not the output pin. So this is going to be our pin 6. And we want to detect when it's high. So that's the amount of time it takes to come back. We want to turn that into a distance using the speed of sound. And so in order to do that, so there's two things going on here. You have to account for the speed of sound, and then you have to also account for the fact that we just want the distance from the transducer to the object. But remember that this sound pulse has to go to the object and then back. So whatever we get, we have to divide that distance by 2. Are you with me on that?
I'm assuming the velocity is going to be speed of sound.
Correct. And so this calculation says lowercase distance is equal to, and we'll go duration times 0.0343, and then divided by 2. And then this is the distance. We want to see this distance as time goes by. So we're going to go, capital serial dot print. So we're going to repeatedly print this distance onto the screen. And first we're going to say, we're just going to make this format nice. So we're going to type out distance, colon. Everything in the quotes is just going to be printed directly to the screen, exactly as written. And actually put a space in here too. Otherwise it's going to look weird. So distance, colon, space, and then quotes. And then we'll go capital serial dot print line. So lowercase print ln. And we want to go distance. And so if this works, every time through the loop, it's going to send out a pulse. It's going to measure how long it takes to bounce back. It's going to use that to calculate a distance, and then it's going to print it up onto our serial screen on the computer. And then this all happens so fast, we're going to delay for 1/10 of a second. So the last command in the loop is delay. We're just going to wait 1/10 of a second, 100. So delay happens in milliseconds. So 100 milliseconds is 100. 100 milliseconds is 1/10 of a second. I don't think that that's a command. I think they only have microseconds, and the default is milliseconds. Now we're done with our loop. Now we can close the squiggly brackets. And so plug your board into the computer like we did last class. And first do compile, see if it registers any errors. If it doesn't, load it on there. And we'll see what happens. Let's do an LED instead of a transistor for now. That'll be quicker. Okay. So now we want to make it so I think this appears to be printing out in centimeters, right? I think that's what it looked like to me. So let's say if your hand gets within 2 centimeters. So if the distance is less than 2, we want to turn on another pin. So let's do another pin mode. And might as well make it pin 5. So let's go pin mode, and we want pin 5. And do we want it to be output or input if we're turning on an LED? Output. And don't forget the semicolon. And now we're gonna go in here and edit the loop. So now we want to say if distance is less than 2.0, then we want to turn pin 5 high, so digital write. And we want this to be pin 5, and we want it to be high. That's all we want to do there. We also want it to turn the LED to turn off if it's equal or greater than 2. So I'm going to just put else. So in all other cases, we're going to say digital write 5 low. And then let's move this delay from here to the end. Okay, that delay is just saying before you repeat the whole cycle again, wait 1/10 of a second. And now, in addition to the wiring that you currently have, so put in this additional wiring. So you want to go from your board, pin 5, and you want to go to, so let me draw the breadboard. And we have the positive power rail and the negative power rail. And let's go, we'll put a 330 ohm resistor here. So that's the one that's orange, orange, brown. And then we'll put an LED. And then we'll send the negative. I didn't make this connection yet. And we'll go from the negative of the LED to the ground, which is this rail. And that should be it. I think that should work. So if you load that onto your board, and move your hand around, when you get within 2 centimeters, the LED should turn on, and then it should turn back off when you get farther away than 2 centimeters. So let me know how it goes. Did you guys get it working? Oh,
I would recommend a larger distance like that. So that
Then-
if you get too close to the center, the numbers are gonna get really unthick.
oh. Yeah, you could try a different number, 5 centimeters or something.
It says else would not be this if. I don't. You can do it. I like how, the leg.
Oh, this that semicolon shouldn't be there. It's so picky about stuff. Not that one. That one's good. The one with the
Is this supposed to turn on?
So just get that out of there and try it again. See.
Yeah.
But it's not working.
Somebody can borrow it there.
This is good.
It's trying to start the Red Sea.
It's reading go right. You know, right. But it is a local meter.
Oh, this is for, you need another one to end the loop, I think.
Oh, zero
You
is
just
like
need to
two.
complete bracket.
Yeah.
Anybody getting this working yet? Okay. So, in order to do, we sort of ran out of time today. But in order to, if instead of an LED, you wanted to power a big machine, you would just have to, instead of having that pin 5 going to the LED, you'd have the pin 5 going to the base of a transistor. And then that would determine whether electricity flowed in your big energy circuit.
But if you think about it, it's reading 0 and it's less than 2. So technically it's high.
Weird.
Okay, well, that's it for today.
Maybe it's.
Will you
not
please,
reading at all.
put,
Maybe that's true.
give me back the stuff I gave you, put the stuff that was in the kits back in the kits. And, this week will mostly just be time working on, a plan for the robot top. And, do you guys have that board? It was you that had the board? No, you had the board. Okay. So. Yeah.
Yes, I don't know.
You know, there's a LED.
Oh, you did.
Here are the keywords that they get. And then there's a lot of trial and error for like, is this the right thing? Does this syntax matter?
Yeah, you have to remember the right direction.
And there's like, what?
Is it at 2? Let's set it a little bigger.
We have the sensors. Is that
I need those sensors back. Yeah.
Clean job. Well,
Okay.
something was written somewhere.
I assume that those that was time for all 3 of us.
3,000.
Oh, wait. No. Oh my God, it's acting squirrely.
3,000.
It's acting crazy.
How do we get 3,000?
Oh, now it's like intermittent. I wonder if some wiring is like not like it's not like or something.
It's not.
No, it's not right.
Why are we?
Yelling still in my
3,000.
3,000.
That's a reading. These.
Yeah, let's,
You won't realize.
Kidding.
Real quick, did you just want to put this in the?
there is a box, yeah, I think I took your box. You can take, take it out of that one and I'll, okay, so let's see, we got 5. Going to this. Let's go. Green is my lucky. It's the luck of the Irish. Okay, so we're gonna go
Like a table.
positive.
It's just already not for the project.
I'm thinking about my paint.
I just.
Yeah. Let's just in case 5 is. Oh, there's nothing going to, oh yeah, there's. You can try, sure.
Can you create?
I'm following those.
Seems like.
Yeah, be sure to like send your name.
Orange, brown.
Yep.
Last week, and then they, you're flagging out. So my part. Right, so then the tire spins with the giant wheel.
Right.
To blame the road.
Everything's bad today.
I know, it messes with your head because you're like, what kind of things could go wrong
And
here?
then we also lack a pension.
Exactly.
Yeah.
You've got a pen?
Reading 1,000.
They had an idea, but
I know.
it's fun.
You guys have to go.
Oh, yeah.
Okay.
Yeah, but he didn't.
Well, you have to believe me, you can do this.
I mean,
That's-
I think we understand the concept.
Yeah.
Or they like.
Okay. You gotta go. I'm gonna
You
try.
can run really fast and go.
Yeah. I'll try every LED. Oh, okay. What are you taking, physics 2?
What's the next class?
What?
What's your next class?
Oh, you.
Oh, 2?
Who teaches that?
At first, what's that?
Did you?
First grant.
I don't know.
I checked the fingers in. It's like.
Uh-huh. Yeah, I like it.
I'm gonna.
I should explain things pretty well.
Good.
Are you just taking the regular class?
I don't use social.
Or,
He's
Oh,
taking
no.
physics.
We're taking the health one. Sort of science.
yeah.
Oh, yeah.
Okay. Okay, yeah.
I
I yeah.
Oh.
I don't remember. He's good.
Everyone loves Sue.
Okay, yeah. I'll keep that in mind.
Yeah, for sure.
Just for today.
I'm just very, yeah.
Oh, yes, measuring like very fast.
Okay.
Oh, yeah, I think,
I think
There
it's
you go.
I have exam.
Yeah, no, that's, well,
It is going, why is it so dim?
Why is it so clear? Now, is there a way to increase the weight of all 5?
Yeah, 5 is the max. I mean, what you can do is, you can decrease the,
Oh, I see. For the,
Increase the weight.
you can change the resistance.
Lower?
Make it lower to make,
For
to make the current.
Makes it work.
Okay, I'll message you.
no, I have one more.
Where do you find it? No, I can't tell. Yeah. Right. Okay. It's reading, so. It's not imposed.
Yeah.
There was
That just changes how fast the signal can be. So, that's important for some stuff. It shouldn't. Yeah. I mean, sometimes these pins go, we've tried multiple times.
Go through the wall.
Here, change it to, change it to 2.
Yeah.
That's kind of terrible. Alright. Anything on it? You definitely don't need all of it. You just have the numbers very.
But that also works as with the
We can make it up to.
horizontal. That doesn't work.
No.
Yeah, something like that.
But it seems like every problem has that.
Well, that was.
Yeah.
That's what I'm hoping for.
If we get lucky.
Yeah.
Do we need a flagpole in there?
No, that's good.
Yeah.
Oh, whoa. Take the
outside?
delay and put it, no, put the delay between those two.
Between the house?
No, after the last digital, right, for after you get everything else. But before that.
Is instead of measuring, the force, we measure the flow and of the block by using a,
Well, is it on,
You're right.
We took out the delay from the last one.
So what you can do is you can.
I don't think that would affect it.
Block, extend.
Yeah, and then
push the block.
on the block will slowly start to.
So annoying.
It is. We're getting close, right?
Yeah, exactly.
The distance and then drive the speed and accelerate.
How much would one of those cost?
That's the problem. It's not the price that's the problem, it's the strength of the.
They,
Actually, yeah, to be fair, I don't know.
Because
oh, we could try, why not try another resistor? We tried everything else, right? Here, let's try,
Did we swap out resistor yet or not yet?
I don't think so. Well, not while I was here anyways.
I would say,
It might be too strong for the action though.
that's what I was.
Do we have a weaker resistor?
Not in the
Just
kit.
frictional force, the normal force will.
Oh, it's 330 the lowest?
And then coefficient.
In the kit.
Friction.
I see.
We have a whole
Usually,
wall
I'm
of
assuming that we're not going to have something
things,
that's per
but-
kilogram.
No.
And also, kinetic friction coefficients are generally less than 1.
Yeah.
Which means that we have to have something,
Oh,
we have to have such a massive
it's
force.
reading.
Yeah, that's kind of what I also thought why
electricity doesn't work.
we should have all the time.
Unless you can find like a.
I think it's the table of burn something.
Yeah,
The physics cut.
exactly.
Find those that are for like big doors.
Yeah, but those, the cover doors is still heavier than the roof.
I know, and so, yeah.
Find like a super weak.
I know there's gotta be just a simple solution somewhere.
The code. Resistance to.
Oh, let me just try the. Let me just try going. So what would happen if we just go?
That's about it.
We have an outside.
I have the past section here too. That.
So that goes in.
Oh.
So it's not the LED or the resistor. It's that
There's not really many people that sort of.
pin. It's not getting.
I'm just like whatever.
Pin 1 7.
I'll post it. Okay.
Oh, do we have to define pin mode 2?
the silent room.
Easy money.
Oh, yeah.
Oh, yeah.
Oh.
Do they like check on?
Yeah.
On your phone or anything? It doesn't matter if I'm on it.
Yeah, good thing.
Oh, and like you are
Nice.
to get
And
out.
put it also is.
We went out with here.
Good thing is fine.
Oh, there we go.
But yeah, they do.
It's gonna work now. It's
Let's
so
go.
amazing.
Okay, ready?
Yeah.
You know what, Guile?
Hi.
Van's roll number 8.
Okay.
Try. Yes. Yes. Good. Oh my god.
Did you assign robot kids today?
No one's checked
Oh,
any
okay,
out
okay.
yet.
Van stole number 8 from you, so I'm gonna have to.
Oh,
still
okay.
assign him.
I noticed there was a different tile size.
This LED is dead. You want the?
I'll take it.
You take it. Want me to tell you what box came out of, or?
No, that's all right.
Okay,
Cool. Thank you.
Oh, this one's bad too.
Okay.
Let's go with the.
Nice. Last week I
Oh, nice.
submitted one homework assignment today.
Okay.
I sent you an email. with
Okay,
the assignment.
is it in the folder or did you email it? I'm way behind on grading the stuff people have emailed, but I will get to those.
I
but-
can't remember. I'll
Okay.
check again.
If it's in the folder, then no problem at all. I
Okay.
mean, really, if it's emailed, no problem either, but
Okay.
I.
Got it. Sounds good.
Okay.
Okay.
Yep.
Just making sure that it's not gonna.
Yeah,
Do you have the exams?
yes.
Oh, mine was on top. Nice.
Yeah.
I wanted to ask you a question on
Yeah.
the design project with the report.
Yeah.
I just got my pieces today, so like,
Yeah.
when is it due?
Just try to get it in when you can. There's not real, I don't really have a deadline for it or anything.
Can I get it like on Thursday or Friday?
Yeah, for sure.
Do I just email it to you or what?
Yeah, email it, please.
Thank you.
Sure.
I can sleep tonight.
Exactly. That's how that kind of thing always is. This board doesn't seem to get power, and then,
Okay.
and this sensor doesn't seem to get power.
Which one? Oh, one and a half, okay. Is that one that was,
This,
were these in a kit?
those don't come in. This might have been in a kit, but no one cares.
Okay.
And then, well, you, I didn't get her, so sorry. This was in a kit and I replaced it.
Oh, good,
with
okay. Another one?
another kit.
Oh, no.
I think I might have. I didn't go get one.
I'll just check.
Okay, sorry. I didn't think of it at the time. I should have.
Okay, let me see.
Bring us making for your robot.
I'm gonna recombobulate.
Friction tester.
Fiction test.
That will check for magnetic friction coefficient.
Oh. That'd be nice.
I think it's cool.
Okay,
We'll see if it
okay.
works out though.
I think it's gonna be easy or hard.
Middle.
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 Yeah.
So I know that you used a different output and ground system. Would this work for the schematic? Or do you want me to specifically draw in like here's the voltage source?
Yeah, well, for a schematic, yeah, you should use the symbols. So for a pin, it would be like a circle like that.
Yep.
And then for the ground, it would be this.
Okay, so cool. So I should just.
Because otherwise, that's sort of like kind of halfway between a schematic and a drawing of the, you know what I mean?
Cool, yeah, so I can just fix that real quick then.
Yes, because there's two separate classes. But I'm gonna label them so everybody knows. What those where.
Do this with my touchpad.